Assalamu alaikum. In this lecture we are going to find the inductance of a composite conductor. Now composite conductor is a conductor in which we have more than one strands, like in this figure, and usually the strands are of different material, and also they are electrically parallel. When we were discussing about the conductors that are used in the overhead transmission lines, I talked about AC SR conductors, aluminium conductor, steel reinforced, and we wrote 24/7 in front of it, and I told you guys that the 24 number is actually the number of aluminium strands and 7 is actually the number of steel strands. So this ACSR conductor is actually a composite conductor, and usually we have steel strands for strength increment, and usually we use composite conductor because the strands will reduce the skin effect. But there are different materials, and steel has more resistance than the aluminium strands, so therefore we basically have higher basic resistance per unit length in terms of composite conductors. So now, as I told you earlier, that we are going to find the inductance of a composite conductor. So we will be starting from two different type of conductors. The first one is conductor X and the other one is conductor Y. And if we will assume that this is a single phase line which is actually having a composite conductors, so conductor X will be the forward conductor, I am assuming that, and the conductor Y is the return conductor. And there are 4 strands in conductor X and there are 4 strands in conductor Y as well. The strands of conductor X are A, B, C, N, and for conductor Y they are A dash, B dash, C dash and M. And as I defined earlier, that for the composite conductor all the strands should be electrically parallel. So all these N strands are electrically parallel and all these M strands are electrically parallel. And as it is the return conductor, so if I assume that the current I is flowing through conductor X, then the same current I will be flowing in conductor Y but in opposite direction. As a starting point, I am considering that all the filaments are of same material. Right, so if all the filaments are of same material, then they have same resistance. So if the resistance is same, then the current that will be flowing through all these filaments will be same. So if we have N conductors, then the current that will be flowing through conductor A will be equal to I over N. The current that is flowing through conductor B will be I over N, and till N conductor it will be I over N. So all the conductors, all the filaments in conductor X will have same current flowing through them, and the current that is flowing through the whole conductor X divided by the total number of conductors is the current actually flowing through the individual filament. Right, so the assumption that we made is that all the conductors are of same material, all the filaments are of same material in a particular conductor, so they will have the same current flowing through that, and as per the definition of composite conductor, all these filaments will be in parallel to each other. Now if we have to find the flux linkage of a certain for example, if I will say this is lambda N, flux linkage of lambda A. So if I say that we have to find the flux linkage of this filament A in all these filament vicinity, like this is the same case if I have to refer it to the last lecture. This is the same case in which we have found a flux linkage of a single conductor in a group of conductors. So this is the same formula that we derived in the last lecture. So flux linkage of conductor A in conductor X in which we have more than one filament. So the formula was This was the formula that we derived in the last lecture. 2 into 10 raised to minus 7 I by n. So this was the current, because in that case we were considering different currents in different filaments. So if we have different currents, then we have to use different currents here, I1, I2, I3, In. But in this case we have the same current flowing through all the filaments. So that is I by n. So I have taken it common and have brought it outside the brackets. And now inside the brackets we only have natural log of 1 over Ra dash, that is the fictitious radius of a conductor, then the distance between A and B, then the distance between A and C, and lastly the distance between A and N. So this is the equation for conductor X, and this part of the equation is actually for conductor Y. The current, again we have m conductors, so the current is being divided into m parts, and after that we have taken it common and brought it outside the brackets. Now we have a negative sign here because this is the return conductor, so the current will be in the opposite direction. Now if we have to simplify this equation, we know that there is 1 by n term here and minus 1 by m term in this part of the equation, right? And we have a natural log here, and there is a summation between the natural logs. So all these part of the equations, 1 by dn, 1 by dab, 1 by r dash, they can be written in the multiplication form and with only one natural log, right? Similarly for this part of the equation. So if I have to just simplify it, we can write the equation will become 2 into 10 raised to minus 7 I, the current, ln 1 over Ra dash plus 1 over dab up to 1 over dan, and 1 by n will be in power of these variables. Similarly, the second part will be minus this minus sign ln into 1 over daa dash plus 1 over dab dash 1 over dam, and the power is 1 by m, right? And now this power can be converted into root of this value. Similarly, this 1 by m will be the root of this value, mth root, this will be the mth root, and this will be the nth root of these values respectively. So the final equation after solving it down will be 2 into 10 raised to minus 7 I into ln m daa dash dab dash up to dam divided by nth root Ra dash dab up to dan, and the unit will be Weber turns per meter. So this will be the flux linkage value for conductor A, this conductor in a group of conductors, right? So now if we have to find the inductance, if we will go to the next slide, so this is the flux linkage value that we calculated on the last slide. So now if we have to calculate the flux, the inductance for conductor number A, what we have to do, we just have to divide it by the current that is flowing through that conductor. So as all the conductors have same current flowing through them, so the current is I by n, so we will be dividing lambda A divided by I by n. So if we will divide this equation by I by n, I will cancel out and n will go into the numerator. So this is 2n into 10 raised to minus 7. The remaining part of the equation will remain same. So using this equation, we can write the formulas for the conductors other than A inductance. So the inductance of conductor B will be lambda B, which is flux linkage of conductor B in a group of conductor, divided by the current that is flowing through that particular conductor. and I'm just changing some variables here. So remaining part of the equation will remain same, 2n into 10 raised to minus 7 ln mn. M is the number of conductors in conductor Y, n is the number of conductors in conductor X. So dBA, in here it was daa dash, so now we are talking about the conductor number B, and we are finding the inductance of conductor B, so that will be dBA dash dBB dash. All the terms of A will be replaced by B, and in denominator RA dash will be moved to the B position, so it will be RB dash. So distance from B to A, RB dash, distance from B to C, and all these values will be multiplied. So this will be the inductance value of conductor number B. Similarly, we can find all the inductance values for all the conductors from A, B up to N, right? As we know that all the filaments have same size and also the same material, so that's why the inductance of all the filaments will be same, right? And if the inductance is same and also they are electrically parallel, so they are connected in parallel electrically, so we can say that the conductor inductance, for example, this is the inductance of conductor X, that will be the filament inductance divided by N. So from circuit analysis, we know that if we have two resistances, for example R1 and R2, and both have the same resistance, for example, for instance it has 1 ohm resistance, R1 also is of 1 ohm, R2 is also of 1 ohm, then if we have to find the parallel combination of these resistances, that will be 1 by 2, because we have two resistances. So if we will have 3 resistances, then it will be divided by 1 by 3, right? So in this case all the inductances will be same, so we will have to just divide L filament, whatever the value of one of these inductance, by divided by the total number of filaments in the conductor. So we have n number of filaments in the conductor number X, so that's why we are dividing L filament, the inductance of one filament, divided by the total number of filaments in conductor number X. So if you have to find inductance of a conductor which has filaments of same size and also of same material, then they will have the same current flowing through them, so therefore they are electrically parallel, as we know from the composite conductor definition. So we just have to find the inductance of one filament and divided it with total number of filaments in the conductor. But what we have to find the inductance of a composite conductor, and in composite conductor we do not have the same material for all the filaments, so the current from all the filaments will not be same, so there will be different current flowing from different filaments. Like for ACSR, the current flowing from the aluminium conductors and the current flowing from the steel conductor will be different. So we cannot say that the inductance for all the filaments will be same, because they will have different current flowing through them, so they will have different inductances, also they will have different resistance as well. So what we have to do, we will find the inductances individually for all the different filaments, and then we will find the average of that. And once we have the average inductance, we will assume that each filament, it can be either of aluminium or it can be either of steel, so they will have the same inductance that is actually equal to the average inductance. For example, for instance, if I just have to explain it a little further, for example, we have one filament of aluminium and the other filament of steel, right? So rather than assuming that it has inductance LA, it has inductance LB. So rather than calculating each inductance individually and then finding the parallel combination of those, what we are doing, we are just finding the L average. So this will be equal to L average, and we can replace this L average. We can say that inductance of this A filament will be L average, and the inductance of this S filament will be L average. So we are not denoting them with their actual inductances, but we are assuming that all the filaments will have same inductance that is actually equal to L average, right? And now if we have n filaments and all has the inductance value of L average, then if we have to find the parallel combination of n L average inductances, then you have to divide L average by n. So this is the same concept that we have applied here, right? So now when we are considering the composite conductor, we are dividing it by n square. One n for taking the average value, and the other n is to find the parallel combination. But in the case of first example, in which we were not taking the composite conductor, we only have one n in the denominator. This is the formula when we are not considering the composite conductor, and this is the case when we are considering the composite conductor, right? So in this case, I by n, we will be dividing it 2n into 10 raised to minus 7 by n square. So 1n will be cancelling out, and we have 1 by n multiplier here. So this 1 by n will go with this m and this n. So this will become mn, and this will become n square. And inside this root value, we have the distances between the conductor's filaments. So this is a dash. If I will just quickly draw the conductor. So this was your x conductor, this was your y conductor. So this is your y, this is a, b, c, and a dash, b dash, c dash, m, right? So in numerator, what we are having is daa dash. So this is the distance between these two filaments, and then dab dash is actually the distance from a to b dash. Similarly here, b to a dash, b, a dash, b to b dash. So in numerator, what we are having is actually the distance between the filaments of two different conductors, x and y, daa dash. But in denominator, what we have is daa. So this is actually the distance of a with itself. So it is actually the radius ra dash. So this value is actually ra dash. Then the distance between a and b. So this is the distance between a and b. Then distance between a and c, distance between a and n. So in numerator, we are having the distances between filaments of different conductors. But in denominator, we have distances between filaments of same conductor. Right? So these terms in the numerator, we can say the numerator is actually GMD, geometric mean distance, as it was the distance between the filaments of two different conductors, right? And the denominator term is actually GMR, geometric mean radius, because it was the distance between the filaments of the same conductor, right? So this whole term can be replaced by GMD, and the whole term in the denominator can be replaced by GMR. So the formula for the inductance of X conductor is 2 into 10 raised to minus 7 ln GMD over GMR. And in some books the notation is dm over ds. So you just have to remember that in numerator we have the distances between the filaments of different conductor, and in denominator we have distances between the filament of the same conductor. And the multiplying factor here, this is also important. In numerator we have GMT, distance, so geometric mean distance, so it is between two different conductors. So if it is between two different conductors, then the root value will be m into n. So there are two different conductors, so we are getting the distances between two different conductors, so therefore the number of filaments in one conductor and the number of filaments in the other conductor will be multiplied. But in denominator we have geometric mean radius. So geometric mean radius is actually the distance between the filaments of the same conductor, so therefore we have only one conductor and we are taking the square of the number of filaments of that particular conductor. So this is actually the formula for the conductor X inductance. So we have two conductors X and Y, so same formula will be used for the Y conductor as well. But now GMD and GMR values will be different, right? And then if you have to find the total inductance of the single phase line, for example in this case, then you have to just add these two inductances, so that will give you the inductance of the whole line. So this was the derivation of the formula to calculate the inductance of a composite conductor. Thank you.